us start off by discussing how a photon distribution evolves with the expansion of the universe. The motivation for studying this is the fact that we discussed in the last class, that we see that we are sitting in the in a region, we are surrounded by a radiation that has a thermal spectrum. So, the photon distribution is known at, and it is a black body spectrum with temperature 2.736 Kelvin. The question that is of interest now is, how does such a thermal spectrum evolve? How does the photon spectrum distribution evolve with the expansion of the universe? We want to understand this, we want to relate this to things in the early history of the universe, etc. So, that is the question that we shall take up. So, for this we consider a small part of the universe, which we take to be rectangular, of size L. And this size of this region, so this is a cubic box which we are considering, and this size of this region L we assume is much smaller than the curvature, length scale of the curvature of the universe. So, if the universe is spatially curved, or even otherwise the space time would be curved. So, let us take the situation where the universe is spatially curved, then we have seen that we have a curvature length scale L. So, that into the scale factor gives us the proper length of the curvature length scale at any time. So, the box size of the box is assumed to be smaller than that. Now, the electromagnetic field inside this box can be decomposed into modes, right. We are, I am sure, aware of this. So, the electromagnetic wave inside this, electromagnetic field inside this box can be decomposed into modes. These modes are e to the power I k dot r minus omega t, right. Since the box is rectangular, these will be plane waves of this kind. So, we can decompose the electromagnetic field inside the box into a sum of modes with different k values, sum of oscillating waves with different k values. Now, we assume periodic boundary conditions. So, we assume that the universe repeats after this. Okay. This is just a mathematical convenience. So, if you have periodic boundary conditions, your modes cannot be arbitrary. K, if you want periodic boundary conditions, the modes that are allowed are have to be one like this or higher k values. So, these modes, the allowed modes can be quantified like this, 2 pi by L. There will be integer multiples of 2 pi by L. So, if I have a wave only along the x axis, it will be 2 pi by L. Now, there are 3 independent directions. So, there will be in general nx I plus ny j plus nz k, where nx, ny, nz are integers 0, 1, 1, 2, 3, etc. Okay. So, the electromagnetic field inside such a box can be decomposed into such modes, where nx, ny, nz could be 0, 1, 2, 3 integers. Okay. So, we can decompose the electromagnetic field inside the box like this, and the excitations of these modes excitations of these modes we interpret as particles, right. These excitations are quantized, we interpret them as particles, these and called photons. So, the energy of these particles E, okay, is okay. Before that, for these electromagnetic waves, the energy E of a particle, the dispersion relation of each mode is omega is equal to C mod k, right, or C into k. We know all of this. Now, excitations of this of these modes, so electromagnetic, if I have no the amplitude cannot be 0 quantum mechanically, okay, but excitations we interpret as particles, and these have energy h cross omega and the momentum p, which is h cross k. Right, these are the photons. So, excitations of these modes we interpret as particles, photons, and the energy. So, one mode, the energy of the excitations in that mode will be quantized, and they will be quantized in units of h cross omega, and p is h cross k will be the momentum. I can have one such unit, two such units, 3, 4, 5, etc. Okay. So, this is how we describe the electromagnetic field inside this box, this small part, this region of the space. Okay. So, we have assumed that the box size, the region of space that we are dealing, is smaller than the curvature length, but it is considerably larger than the wavelength of the radiation that we are considering. Okay. So, it is larger, but it is larger, L is larger than the wavelength which we are considering. Okay. Now, the question is, what happens with the expansion of the universe? The universe is expanding, we know. So, the whole box itself is going to expand. This is all in physical units, proper distances. So, the whole box is going to expand. So, the next question is, what happens to this whole thing with the expansion? So, we assume that the expansion rate of the universe, so the rate at which the box is expanding, or the expansion rate of the universe, what quantifies the expansion rate of the universe? It is the Hubble parameter, right. So, we assume that the Hubble parameter which quantifies the expansion rate of the universe, h, which is a function of time. So, the expansion rate is much smaller than the frequency of these oscillations. So, each of these mode will have some frequency of oscillation, which is omega, and that is related to the wave number through this speed of light c. So, we assume that the expansion is much slower than the frequency of oscillation of these modes, right. So, we assume that this is much slower, and the frequency is omega by 2 pi. Factors of 2 pi do not matter. So, the expansion rate is assumed to be much smaller. So, by the time many oscillations are completed, the universe has expanded by some percent, okay, and that is quite reasonable, because the radiation we are dealing with, it oscillates, let us say, let us just make an estimate. If I have, let me just make an estimate, what is the value of the frequency for the radiation that we are considering. Let us take 1 millimeter. So, lambda is 10 to the power minus 3 meters. So, the frequency corresponding to that frequency corresponding to this is going to be c by lambda. So, 3 into 10 to the power 8. So, that is going to be 3 into 10 to the power 11. 8 and 3, 11 second inverse hertz, right, 10 to the power 11 hertz. That is the frequency of oscillation. So, 10 to the power 11 second inverse. The Hubble parameter we have seen, if I calculate it in second inverse, it is an extremely small number, right. The inverse of that is gigayears. So, this is an extremely small number. So, this is obviously at present much smaller than the frequency, and even if you go back in the past, there will be a regime where this condition will continue to hold. Now, if this assumption is correct, so we can assume that it is a very slow expansion. So, the expansion, essentially the expansion much slower than oscillation, right. The wave has an oscillation of the electromagnetic field and it is much slower, that is the assumption. So, under this slow expansion, what if the expansion is extremely slow, what we can say is that the photons that are there in these excitations, these photons will not change, the number of photons will not change. Okay. What is going to happen is that just the wavelength of each photon is going to get changed. Okay. That is the basic consequence. So, if the expansion is extremely slow, then what you can say is that the wavelength, the wave, each such mode or wave remains unchanged under the expansion, except that its wavelength and frequency get changed, that is all. Okay. This would not be true if the expansion rate were comparable to the oscillation frequency, but if it is much slower, as it is the case here, we can assume that all that happens due to the expansion is that the wavelength corresponding to a mode gets changed. Okay. And the wavelength gets changed, we know that the wavelength scales proportional to the scale factor. As the universe expands, the wavelength also goes up proportionately. This we have already worked out. So, as the universe expands, the whole wave just scales, the wavelength scales with the expansion of the universe. The same mode, the wavelength just increases. Okay, nothing happens to the number of particles or things like that. So, this is what we are going to assume. So, this is true provided the expansion is much slower than the oscillation. So, if the wavelength increases proportional to A, the wave vector will decrease proportional to the inverse of it will go down as with the expansion of the universe, that is obvious. Okay. Or what we can say from this is that with the expansion of the universe, the momentum of a particle scales as the inverse of the scale factor, because the momentum is h cross k, right. The momentum of a particle of this excitation is h cross k, and k scales as 1 by a. So, the momentum of a particle also scales as 1 by a. Now, this result can also be derived purely classically. You follow the momentum of a particle in the expanding universe and you can derive the same thing, arrive at the same conclusion also classically. The momentum of a particle scales as 1 by a. Okay. Now, so this is the main thing that we are going to need. The momentum of a particle scales as 1 by a with the expansion of the universe. Now, photons, so we have started our discussion with photons, electromagnetic waves, which we have expanded into modes. Now, there could also be massive particles like say neutrinos, okay, or some other particle. So, the analysis that we have carried out is exactly the same even if we had massive particles. The only change that would occur is that the dispersion relation would be different. Okay. So, for a in general for a massive particle, the energy is the square root of p square c square plus m square c4. And this tells us how the energy changes with the expansion of the universe. And here you can, from here you can work out how the frequency changes with the expansion of the universe, because you know that the energy is h cross omega. Okay. So, if I had a massive particle, instead of electromagnetic wave I had some massive say particle which is possibly described by the Klein-Gordon equation or by some other equation. It has a mass, then the energy and the momentum would be related like this, and the dependence on the scale factor would be different, and the frequency would also not scale as 1 by a, but it would be different, but you can work out these things starting from this. So, this is most general, it holds even for massive particles. Okay. So, we have these modes. Now, the question is how many particles are there in each of these modes? That is what we mean by a distribution, right. So, if I had photons for example, or some other particles in thermal equilibrium at a temperature T, the distribution is given. So, let us, what we are considering is a thermal distribution . And I am sure all of you know that in thermal equilibrium the occupation number of any mode n for any mode P is given by 1 by e to the power, or let me write it as exponential E epsilon or energy minus mu by k T plus minus 1. Okay. So, let me again explain to you what we are doing. We started off by considering photons. So, we considered a region of space, and the electromagnetic field inside this region of space we decomposed into mode. The excitations of these modes we identified as particles called photons. Now, the question is that if these photons are in thermal equilibrium at a temperature T, what do we mean by that? This is something we had discussed in the last class. Black body radiation. So, the simplest way to visualize this is I have a cavity surrounded by some medium which can absorb and emit photons with equal efficiency at all frequencies. So, the cavity is maintained at a temperature T. I wait sufficiently long, the photons inside are going to come in thermal equilibrium. Okay. So, just think of this box that we are dealing with as the cavity inside that, for example. Okay. Now, so the photons inside have come to thermal equilibrium with the walls, and these photons, they have different momenta. These are the different modes. of the electromagnetic wave inside. Now, the question that I am asking is how many photons do we expect in each mode? What is the occupation number? This is called the occupation number of each mode. Okay. And this we know from statistical mechanics is given by this distribution, not only for photons, for all kinds of particles in thermal equilibrium. So, let me explain the various terms that occur in this. So, epsilon over here is the energy corresponding to this particle with momentum p. Okay. So, if I know p, I can calculate the energy. For a free particle, we know how to calculate it. I just wrote down the expression, it is given over here. Right. So, I know how to calculate the energy in terms of the momentum. Okay. Now, this mu is the chemical potential. It is a constant that comes about because the number of particles is conserved. Okay. So, if you want to have certain number of if you want to have a certain number of particles at t equal to 0, then you have this, then that is incorporated through this chemical potential. Chemical potential is an arbitrary constant that is allowed in this distribution. Okay. And plus minus 1, there are two kinds of particles, we know that. So, minus are the Dirac particles or the Bose particles, that is a Bose distribution, and plus sign are the fermions. Okay. So, these are called bosons. Particles for which you have a minus sign are called bosons, and you have the Fermi particles plus sign. This is called the Bose-Einstein distribution. If it is minus, it is called the Fermi distribution, Fermi-Dirac distribution if this has a plus sign. Okay. So, the bosons are particles with integer spin. They have the property that the occupation number can assume any value 0, 1, 2, 3, 4, 5, it can have any value. Okay. It could be fraction, that is because it is the expectation value, so it could be fractional also. Okay. So, the predicted occupation number is you could have many particles occupying the same state. Fermi particles have the Pauli exclusion principle. You could either have 0 particle in a state or 1. You cannot have 2 particles occupying the same state. Okay. So, these are for particles which follow the Dirac, these are spin half particles which follow the Pauli exclusion principle, and these are for bosons where many particles can occupy the same state. So, the same mode can have many particles. Okay. Now, photons for photons, let me just tell you this, for photons the chemical potential is 0, there are no conserved. Photons can be destroyed and created, there is no conserved quantity, right. Photons inside can hit the wall and get absorbed, they can also be emitted by the wall, there is no conserved quantity associated with photons. So, for photons the chemical potential is 0. There are other particles with which there are associated conserved quantities, and you cannot destroy and create them at will. So, for those there will be a non-zero chemical potential. Okay. Photons are bosons. So, they are they follow the Bose distribution, they will have a minus sign. But I could apply the same thing even for other particles like neutrinos, which are fermions, so they will have a plus sign. Okay, this is a very general treatment. This is a thermal distribution. If I had a non-thermal distribution, then the occupation number could be anything. Okay, thermal distribution has two parameters. One is the mu, the chemical potential, other is the temperature. This is the temperature. Right, which specify everything about the occupation number, the particle distribution. And the question that we are addressing is how does the particle occupation number or the particle distribution change with the expansion of the universe? That is the question that we are interested in. Okay. So, that is the question we are addressing. Let me get down to this question. Okay, we shall need this, so let me keep it carefully. Fine. So, how does the particle occupation number n p change with the expansion of the universe? That is the basic question. Okay. Now, we assume, I have already told you this, we assume that with the expansion of the universe expands slowly. That is the basic assumption, right, compared to the frequency associated with each of these particles. So, if you assume this, then the particles are not created or destroyed due to the expansion of the universe. There is no change in the particles numbers due to the expansion of the universe. What happens is that the momentum of every particle of every mode, that changes, that gets changed, and that with the expansion it decreases inversely with the scale factor. We know this, right. So, all that happens with the expansion, this is unchanged. All that happens is P scales as 1 by A. So, suppose I tell you that at some t initial there is a scale factor A initial, okay, and the particle distribution is Ni initial, the initial particle distribution as a function of P, right. It could be the thermal distribution, it could be something else, the analysis is general, right. So, at some initial time the particle occupation number is given by this function Ni as a function of P, it is some function, okay, whose functional form I am not specifying. Now, the question that we are asking is, at a later time Tf, where the scale factor has a value Af, what is the final distribution function at okay, what is this function? That is the question we are asking. At some final time Af, final time could precede or even be before this, does not matter. At some other instant Af, Tf, what is the particle distribution? What is the occupation number of a mode P? Now, we know that the functional that this, so we are interested in the occupation number of a mode P at a final time, at the final instant F. Okay. Now, at the initial time Ti, what was the momentum corresponding to this mode, this particle? The momentum was different. Okay. So, this, but the particles have neither been destroyed nor been created. So, what we can say is that this is the initial distribution function evaluated So, let us see. So, this okay, this has a value P at the final instant. What is the value it will have at the initial instant? This is at final. What is the corresponding value at the initial time? So, we know that this scales inversely. So, it is going to be scaled as AI by A f, right. So, the number of photons with the momentum p at the final time is essentially the number of momentum particles with momentum p ai by af at the initial time, right. So, this gives us the relation between the distribution functions, okay, because the particles are not destroyed or neither destroyed nor created. So, you can just relate the photon number at a certain momentum now to the photon number at a different momentum in the past at some other time, that is all. The momentum value has changed. And I have made a mistake here, this should be AF by now how much is it B? Let us just get this clear instead of so the P scales inversely as A, right. So, at some, let us say it has a value, okay. So, P into A is a conserved quantity, P final A final is equal to P initial A initial, or P final is P I A I by A f. So, we want P I, this is going to be A f P f by A I, that we want the initial momentum in terms of the final momentum. So, we are asking, the question that we are asking is how many particles are there with final momentum P. So, this is going to be number of particles with initial momentum. So, this is going to be AF over here by AI, right. Okay, so, that is the relation, we have got it. Let me cut this out, we do not need this, it has been worked out over here. Okay. So, if I know the initial momentum, the final momentum Pf, they are related like this, and the question we are asking is what is the number of particles with final momentum P. This is the same as the number of particles with initial momentum Pi related to the final momentum like this, because the particles do not get destroyed or created, their momentum only changes. Okay. So, this is the initial distribution evaluated at P into AF by AI. Okay. So, let us now see what happens if we have a thermal distribution. So, if I have a thermal distribution to start with, so let us assume that at some time we have a thermal distribution and I want to calculate. So, at the initial instant we have a thermal distribution, that is the assumption. Okay. So, at the initial time Ti we have a thermal distribution what happens with the expansion of the universe. So, if I now want to calculate n, the occupation number at some later time Tf, this is the same thermal. So, at the initial time it is a thermal distribution with temperature T, chemical mu, potential mu, right, that is what specifies the thermal distribution, the temperature and the chemical potential. These are the initial temperature and the initial chemical potential at a time Ti. Okay. Let me put I over here, initial, that is the at the time Ti, this is the thermal distribution with temperature Ti and chemical potential mu I. Now, we want to calculate what is the particle distribution at a time Tf. Okay. So, number of particles in a momentum state P, we have seen we have to take the initial distribution, put in P, not at the value which we are interested, but at a different value, at a value which has been scaled by AF into divided by AI, right. So, the thermal distribution has this form. All that you have to do is you have to replace P over here with Pf by Pi. P occurs in this E. Okay. Now, we will consider a situation which is relativistic, massless particle. Okay. So, this is a point which massless particle m equal to 0. So, m equal to 0, then I have 1 divided by exponential. What is this energy of a particle with momentum p for a massless particle? It is p into c, right. So, I have exponential, instead of p now I will have p into AF by AI minus mu initial by this k is the Boltzmann constant. I should have clarified this earlier. This k is the Boltzmann constant Kb, not the wave number of the mode that we are dealing with, right. This is the Boltzmann constant that occurs in thermodynamics. Okay, Kb into T initial minus 1. So, this is the final particle distribution if the initial particle distribution is a thermal distribution with temperature Ti, chemical potential mu I. Now, you can see that the final particle distribution, the final, let me put a F here if you wish, final particle distribution can be written in terms of a thermal distribution with a different chemical potential and a different temperature. How can we do that? So, what we want to do is we want to write this as 1 by exponential P minus mu F by Kb T. You could have plus minus here, it does not matter, plus minus 1. Okay. You can see that you can easily write it like this, provided you define mu F and Tf in certain way. So, the question is, how will you define mu F and Tf? So, if you define mu F to be equal to AI by AF mu initial and the T final to be AI by AF T final, then plug these in here, you will have extra factors of AI by AF multiplying both of these, which essentially corresponds to AF by AI multiplying this. Okay. So, this we have written like this, which is a thermal distribution with a different temperature and a different chemical potential. So, what do we learn from this exercise? From this exercise what we learned is that if initially my particle distribution, if it is thermal with chemical potential mu initial, temperature T initial, with the expansion of the universe, the final potential, okay. So, the particles are not interacting, that is an assumption I have forgotten to mention. So, what I have assumed is that the only thing that happens is the universe expands. The particles do not collide. If these particles were say colliding with something, then the particle could be moved into a different mode, right. A photon going like this collides with a particle, it could be moving in a different direction. So, the one photon has been destroyed, another photon has been created, right. So, we are assuming that these particles do not interact with anything, there is only the free expansion of the universe. Under this, if I have massless particles, mass m equal to 0, that is an assumption we have made, then the final distribution is also thermal, provided it started off with a thermal distribution, the final distribution is also thermal, and it has a momentum, it has a chemical potential mu f, which is A initial into the initial chemical potential by the, or the chemical potential scales inversely with the scale factor, the final temperature T f is equal to A I by A f T I. The temperature of this thermal of this distribution also scales inversely with the scale factor. Okay. So, I start off with a thermal distribution, the distribution remains thermal, just the temperature gets scaled as inversely with the scale factor, the chemical potential also scales inversely with the scale factor. What is the relevance of this to our discussion? I have told you that the photons that we see here, okay. Let us go back to this picture which we had considered in the last class. We are seeing a thermal distribution of photons here. Now, these photons I have told you do not interact with anything in our neighborhood, all the way to a redshift of order few hundreds and thousand. These photons do not interact, as good as do not interact with anything, because the universe is transparent. Okay. So, but suppose at some very high redshift the photons were in equilibrium with matter, okay. Somehow they came to thermal equilibrium with matter, after which they cease to interact, they just move freely and the universe expands. Then if at some time a thermal distribution was established, the thermal distribution will be seen now also, even if the photons are no longer in thermal contact with anything, they just propagate freely in the expanding universe. Okay, a thermal distribution will also still be maintained. The temperature of this thermal distribution, if at the instant when it was in thermal equilibrium, it was Ti, it had a chemical, photons will not have a chemical potential, then at present or at any later time, the temperature would have scaled as inverse of the scale factor. If there was a chemical potential, it would have scaled as inverse of the scale factor. So, once you have thermal equilibrium and then you just let them move freely after that, then this is how things happen for a massless particle. Okay. Now, let us consider what happens if you have massive particles. So, this is what happens in the situation when you have massless particles, and I have told you what is the significance of this. Now, let us see what happens if you have massive particles. So, this is my distribution. Let us consider this distribution for massive particles. Now, the main difference that occurs when you have massive particles is that the m not equal to 0. So, the difference that occurs is that the energy of the particle is now the square root of m square c4 plus p square c square, right. So, there is an energy even when the momentum is 0. That is the main difference. The energy is mc square. Otherwise, for okay. Now, the quantity that comes in over here is this energy of the particle by kT, Boltzmann constant into the temperature. So, the quantity of interest is this divided by kBT, right. So, this is divided by the Boltzmann constant into T and this we can write as right, this nothing, I have just written it like this. Now, there are two situations which need to be considered separately. The first situation is where the temperature is much higher than the rest mass of the particle mc square. The temperature of the distribution is much higher than the rest mass of the particle. So, if you assume this, then the first term is extremely small, I can neglect it, right, because this is a much larger number than mc square. So, this term can be neglected, and in this situation is approximately equal to Pc by kBT. Okay. So, the mass of the particle is of no consequence, this is as good as m equal to 0. Okay, this is what is called relativistic. Okay. So, if I have a situation that is relativistic, that the temperature is comparable, the energy scale corresponding to the temperature is much higher than the rest mass of the particles, then the fact that the particles have a mass is of no consequence. Okay. And the same thing, the thing that we have analyzed just a short while ago continues to hold. So, the temperature scales as inverse of the scale factor. Okay. Let me take up an example where this is important. Suppose we have neutrinos in the universe. Okay. This is something we shall come to. Whose mass is m. Okay. So, let us now go back to the same picture. Let us assume that the neutrinos were in thermal equilibrium with the rest of the constituents of the universe at some epoch very high, very back in the past. Neutrinos we know are weakly interacting particles, they do not interact much with anything now. So, even if they were there, they would just go through. Okay, but suppose way back in the past at some high redshift, the neutrinos were in thermal equilibrium with the rest of the constituents of the universe. Okay. So, at this high redshift, the temperature of the whole constituents of the universe would be extremely high, right. Suppose at that epoch when the neutrinos were in thermal equilibrium, the temperature kBT was much higher than mc square. Okay. At that epoch the temperature was much higher. Okay. So, then the neutrinos go out of thermal equilibrium. Just like the photons I told you, after some time they go out of thermal equilibrium, they do not interact with anything. So, suppose at this the neutrinos at certain epoch of time go out of thermal equilibrium. Okay. Once they go out of thermal equilibrium, they do not interact with anything, just free expansion. Now, the question that I ask is, what is the neutrino distribution now? Okay. So, this is when they go out of thermal equilibrium in the past, when they decouple. Okay. By decouple, I mean that they are no longer interacting with the rest of the matter. So, at some high temperature in the past, the neutrinos were in equilibrium and then they stop interacting, they decouple. Now, at present the temperature of the universe is much smaller, it is around 3 Kelvin. So, at present Kb temperature is comparable or could be even less than mc square, okay, either of these. So, a neutrino has mass. So, at present the temperature could be comparable or less than, let us consider a situation. Okay. So, the temperature now is 3 Kelvin, it is let us say less than the neutrino mass, but when the neutrino decoupled it was more than the neutrino mass. The question is, what is the neutrino distribution function now? I have told you that with the expansion of the universe, all that happens for what happens is that the distribution function remains unchanged, right. The distribution function does not change, all that happens is that the momentum just changes, okay, the momentum changes. So, if I want to calculate the distribution function of the neutrino now, it will be, what will it be? It will be where this temperature T is related to the temperature at decoupling when they decouple just by the ratio of the scale factors. The chemical potential, sorry, there could be a chemical potential here also. Okay. So, even though if the particles are massive now, their distribution function is going to be relativistic, because the distribution function does not change once the universe, once the particles decouple, once the universe, once these particles just stop interacting with other particles, the distribution function remains fixed, okay, that does not change. So, that is a very important point which is true for neutrinos. For as an example I have showed you this. The next question is if I have massive particles, where if I have a situation where kBt is smaller than mc square, much smaller, right. So, I have a situation where there are particles in thermal equilibrium with kBt much smaller than mc square. Okay. The neutrinos, remember, they are in thermal equilibrium at a situation where kBt is much more than mc square, okay, and then they decouple. Now, the question is what happens when the temperature of the universe falls below mc square, that is a different issue. Now, we are dealing with particles which satisfy this. For example, hydrogen atoms, okay, just as at hydrogen atoms. In, let us say, in equilibrium or whatever with the CMBR or some such thing, okay, cosmic microwave background radiation. Not in equilibrium, but hydrogen atoms in thermal equilibrium with each other, CMBR does not come into the picture, okay. And the temperature is much smaller, the situation we are considering. So, hydrogen atom in some, say, which fills some part of the universe, okay. Now, the temperature is much smaller than the mass into c square. So, this is something I will take up in the next class. Let me stop here for today and resume in the next class.